Throw Alexa to the bin. Today I'm gonna show you how to make your own virtual assistant from home, from scratch. Forget about all those expensive subscriptions. You're not gonna pay anything, even the electricity bill. Say hello to my solar. A very cheap tool, ESP32. This guy is less than a few dollars. Just don't drink the coffee in the Starbucks for tomorrow and you're gonna get one of these. And then the next you need is obviously sensors. I'm going to be using some soil moisture sensors, so I'm going to use it for agriculture, but you can use it for your bathroom or pranking your neighbors. Now we are going to build our own battery to supply the service, and obviously we are not going to see the sun every day. Obviously sometimes all of us have some moody days, it's our earth. So we have this adapter. This is just a laptop adapter. Just use this to save our life when we don't see the sun for those days, you know, those rainy, moody days. And then we are gonna take all the information from here, send it through our ESP and to the Wi-Fi, and using Wi-Fi is gonna go to MQTT server. We are gonna come to all those confusing things. What are they? I'm gonna be telling about it. Now our virtual assistant is gonna work for us, and then it's gonna run whatever it is. It can turn your coffee machine on, it can water your flowers, it can prank your neighbor. Hello. It can tell the burglars stay away from your property. So you can use it for everything and anything you want. Let's get to the business and see how we are going to build it today. Let's check schematics. Now we have our inputs and outputs on the paper. Everything is written as you can see. Adapter, solar panel, 4S3P battery, total 16.8 volts, ESP32 sensors and pump. The sensors are our ears here, letting us know the data through ESP32 and giving analog values. Then we are transmitting them through Wi-Fi to our database using Mosquitto MQTT protocol. Then N8 combines these data and weather information using API, sending it to AI and coming up with a decision. Then we send this decision to user using Telegram, then all the way back to ESP32, and ESP32 executes this decision whether to run the pump or not. So this system uses something called power ORing. Basically multiple power sources feed the same circuit, in our case solar and adapter, but diodes make sure only the higher voltage source is actually used, and they prevent current from flowing backward into the other supplies. That means I can safely combine my adapter, battery and regulators without them fighting each other. Automatic source selection, zero risk of backfeeding, and stable power delivery. It's one of the most important tricks in power electronics. Designing the battery case was honestly one of the hardest parts of this whole project. On paper everything was perfect. I measured the cells with a caliper, modeled the case and hit print. In real life the cells refused to fit. The problem was tolerance. The caliper, the battery and the 3D printer all disagree just enough to completely break your design. So I redesigned it, printed again, still wrong, over and over. After almost 5 hours of trial and error, I finally got the fit right. Then I left a 2mm gap between every cell for airflow, removed the sidewalls so heat could escape, and added a separate holder for the BMS and charging circuit so everything stays fixed, safe, and protected from short circuits. Painful, but totally worth it. Once the case finally worked, the battery assembly was the satisfying part. The cells fit perfectly, the spacing allows airflow to manage heat, and I added a charge percentage indicator, so with one button I press, I always know the battery level without opening the enclosure. Here I am testing the battery for the last time before I continue to assemble the circuit. This is the heart of the system. The power circuit is designed so 3 energy sources, the adapter, the solar panel and the battery work together without ever interfering with each other. First, the adapter and solar panel go through an ORing stage, which automatically selects whichever one has the highest voltage and prevents reverse current. Right after that point, the power line splits. One branch becomes the main system bus and the other runs through CCCV charging module that safely charges the battery with proper current and voltage control. The battery's output is then protected by a BMS and connected back to the main bus through a second ORing stage. This means if external power ever disappears, the battery takes over instantly in milliseconds, without any reset or interruption happening for our ESP32. On the second board, 3 LM2596 converters generate precise 5 volts, 3 volts, and 12 volts for the ESP32, the sensors, and the pump, while the transistor-driven relay ensures the pump only receives power when the system explicitly allows it. Every path is controlled, isolated, and engineered for long-term reliability, and this is the most important part of this system, because this is gonna save us so much energy in the long run. Here I'm setting up the CCCV unit and seeing if it charges our battery correctly, and everything looks awesome. Unfortunately, it's hard to see on the camera since these are LEDs that are turning on and off in a very high frequency. My camera is not able to capture it correctly, but still you can see that it is giving me 0.7 amps almost, and on a 16.7 voltage, which is like CCCV. So right now it's giving me constant current because my battery is almost full. It is charging perfectly, there is no heating, and everything looks healthy on the system. And tidy up around, so we get ready for the software and the last test for the project, and we are gonna see if the house is gonna flood or my flowers are gonna grow in peace in my garden after this. I've completed the test software for the ESP32. Here we are telling that read the sensor values, wait for 25 seconds, write them on the board, and then wait for another 5 seconds, then test the sensors once more. And here you see the values. All of them read 4095, which is the highest value it can read, which means 0% humidity, because all my sensors are already outside the water and all of them are dry. So it shows that our sensor readings are correct, so which means we can continue. Once the hardware was alive, it was time to give the system a brain. I installed Docker and built the entire backend as containerized services. One container running Mosquitto as the MQTT broker and another running N8N as the automation engine. After launching the containers, I verified the MQTT stack directly from the terminal by creating a publisher and subscriber, basically a master and a slave, and confirmed that messages were flowing correctly through the broker. Then I flashed the ESP32 with new firmware so it could start publishing live sensor data to the MQTT server and listen for the pump control commands. At that point, the physical system and the cloud were officially talking to each other. To visualize the system, I installed MQTT Explorer, which gives a real-time graphical view of every topic, payload, and device on the network. This made debugging incredibly fast and reliable. With the communication layer stable, I built the automation logic in N8N. Incoming sensor values trigger decision nodes, the AI module analyzes the data, and the system sends a message to the user through a Telegram bot asking for confirmation before activating the irrigation. Once the user approves, a control message is published back to the ESP32 and the pump runs for the exact duration requested. From soil to cloud to phone and back to water, the full loop is closed. And yes, I preferred Telegram because it was cheap. By telling cheap, I mean it's free. And yes, again, this was the moment I finally trusted the system enough to leave it alone for 5 minutes. And yes, it works correctly. So I removed the human approval. Now it just runs in the background. Still, it just decides by itself. With the hardware finished and the software stable, it was time to move the system into the real world. I built a small 3 square meter test garden, planted garlic, installed the pump, placed the sensors, and let the system take control. From that moment on, the system ran completely on its own, reading the soil, making decisions, communicating with the cloud, requesting approval through my phone, and delivering water only when it was truly needed. Then I also removed the approval because it was not necessary, it was so accurate. I let it run for an entire week. The battery stayed fully charged and healthy. There was no measurable voltage drop. The total energy consumption was as low as 16 watts. Since the times when the ESP32 is not working, it is in deep sleep mode. And the entire system used only less than 500 milliliters of water entire week. And even after all that time, it still sends real-time notifications to my phone. This is no longer just a prototype, it's a working system. I'm planning to scale this project, add more features, and evolve it into a full product. Because this is what engineering is about. Building something that works, survives, and matters. From an idea to electrons to real food.